Okay, sure. Hello, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my great honor to introduce our prestigious speaker, Professor Jorge Nocedal. Professor Nocedal is Walter P. Murphy Professor of Industrial Engineering and Management Science and Engineering Sciences and Applied Math at Northwestern University. He has made fundamental contributions to optimization, applied mathematics, and operations research. Professor Nocedal has won numerous awards. In 1998, he was the invited speaker to the International Congress of Mathematicians in Berlin. He was named an ISI highly cited researcher in 2004. He has also received the George Danzig Prize and Charles Brydon Prize, John von Neumann Theory Prize. He is also a SIAM Fellow. More recently, he was elected to the National Academy of Engineering in 2020. And and without further ado, the talk of his title is Derivative-Free Optimization of Noisy Function. Without further ado, please join me in welcoming him.
All right, thanks very much, young people. It's a great idea that you're organizing this online seminar. I'm trying to share my screen, but is it happening? Oh yeah, I think it's happening now. This talk is going to be, I'm sure, much less theoretical than some of the talks that you have had here, but I will explain why and how we approach things. Okay, so first of all, I'm trying to present a summary of 3 papers presented by here my former student and collaborators who did the bulk of the work. And the problem is, as you imagine, we have a function phi that in principle we want to minimize, but whose derivative cannot be computed. We just don't have the derivative of the function phi. And to make it as simple as possible, we're going to assume that phi is a smooth function. It's twice differentiable. It could be just like a quadratic function in 100 variables or some other simple function. But what's going to make it interesting here is that every time we try to observe the function, we observe a noisy version of it, and we're going to denote the noise by E of x. So the problem is, how do we minimize the original function f while observing only the noisy function phi, while observing only the noisy function f? So this is the typical black box setting. And I have to mention here to statisticians that we're interested in both deterministic noise and stochastic noise. And some people say, what is deterministic noise? And we can get into discussion about that if you're interested. But an example of deterministic noise is round-off error. But a property of deterministic noise is if you evaluate the function at the same point, it always gives you the same value. But if you move a little bit, then the function changes. That's what happens, for instance, with round-off error. And deterministic noise arises in a lot of scientific computations. All right, so derivative-free optimization really has received a lot of attention in the last 3 decades. And quite surprisingly, most of the emphasis has been on unconstrained minimization problem and also on the noiseless setting. There's been surprisingly lack of comparative testing among the methods until what I consider a landmark paper came in 2001 by Moret and Wild that, in my opinion, destroyed a lot of myths about methods that had pattern search methods, Nelder-Mead method, for these classes of problems that were clearly inferior to something that we call the interpolation-based trust region method. So Powell proposed this method, and in the study of Moret and Wild, it showed to be superior both for smooth, non-smooth, and noisy objective functions. And this is something we suspected because, as I will explain in a moment, this method really is quite intelligent. It uses the information in a really good way. So our conclusion after reading this paper in 2009 is that this Powell approach represents the state of the art for derivative-free optimization of underlying smooth functions. Now, I'm going to be talking about local algorithms. I'm not going to be talking about global optimization. Now, global optimization is often done via a combination of methods. And therefore, I'm going to just deal with how do you compute efficiently a local solution. And then you can combine it sometimes with research, and you can get competitive global algorithms. Now, we will see that complexity here is not very useful in guiding us to the right algorithms. And when you talk about derivative-free optimization, people often ask the question, how does what you do compare with Bayesian optimization? And I will not discuss this here because I view Bayesian optimization as geared for global optimization of small dimensional problems. And here I'm dealing with local algorithms, and I'm very interested in scalability. I think until a few years ago, there were no efficient algorithms for solving derivative-free optimization in thousands of variables. But now I think I'll show you how one can do that in a robust and reliable way. So Bayesian optimization and global optimization is something I would like to be discussing in the near future, how these methods compare. So I want to present this method developed by Powell and elaborated over a number of years by people here. It's based on interpolation. So what the method does is, first of all, it gets a number of samples. The value is the function in a stencil. Then it constructs a quadratic model that interpolates the observed function values. The quadratic model, here's the quadratic model that you've created, is then minimized subject to a trust region constraint. This is the trust region method. And this minimum of this quadratic model over the trust region wall is going to give you the new iterate xk plus 1. Now, in order to construct this model, you need to know what the matrix B is and what the vector G is. And if you're going to do that just by interpolation, you're going to need of this order of n squared function values to define a quadratic model. And that's a lot of information, not if the number of variables is 4 or 10, but it's going to be a really impossible task if the number of variables is 100. But Powell proposed a very clever way of reducing the number of interpolation points by infusing this idea with underlying Quasi-Newton technology. What he did is he required only order n interpolation points, but then decided to define the new approximation to the Hessian of the quadratic model as the one that is closest to the previous approximation, subject to interpolating 2n plus 1 function values. What is the matrix B and the vector G? Matrix B and the vector G, such that B is as close as possible to our previous approximation, and you interpolate 2 endpoints. In this way, he's able to get the arithmetic complexity to n squared. Here is going to be of order n to the 6 if you're not careful. But by doing clever updating of factorizations, he is able to maintain a method that does only O(n) squared work. So what happens after you compute a new point xk plus 1? Then you add xk plus 1, remove one of the interpolation points, and only retain 2n plus 1 as you continue. And so the method interpolates, minimizes, interpolates, minimizes subject to the trust region. And the trust region is shrinking as you're converging to the solution. And the method works quite well. Now, there are a few drawbacks about this approach. Once you start generating points, you don't have control about where they're going to lie, and they tend to lie. The iterates you generate tend to lie in a subspace. And therefore, what they do is they go towards a solution, they keep generating points, and when they see that the interpolation points are close to being in a subspace, then they create a special phase that spaces out points. They create iterations that build points that are perpendicular to the space that you are, because interpolating in lower dimensional subspace is an ill-conditioned and ill-defined problem. So therefore, one has to add a geometry improving phase to this algorithm, complicating it. Now, the implementation, in order to get n-squared operations, is really complicated. And there's only one code that does that, the code of Powell, that can do this factorization in a robust manner, because there are questions about linear algebra that are tricky here. And the other thing is extending this approach to general constraints has not proved to be simple. And in fact, even though Mike Powell worked on this topic for more than 15 years, he was able to extend this method only to bound constraints, but never to general constraints. Finally, this point generates one point at a time, and as a result, does not parallelize well. Nevertheless, it is a really impressive method that I'm going to keep in the background, and it's going to be the benchmark to what we are going to be doing. Okay, one surprising observation is that this approach of Powell works surprisingly well when you do noisy functions. And even though it does interpolation, you would say you don't do interpolation if you have noisy functions. There is a reason for that. You know, you construct your quadratic model using only two endpoints. And then after you take a step D, after taking a step D, you see how the true objective and the model changed, how they diminished. And if this ratio is close to 1, you expand the trust region, otherwise you contract it. So one of the problems of interpolation noisy functions is that if you put interpolating points too close, or what you're doing is interpolating noise and creating a really terrible quadratic ball. So in words here, or with my hands, the secret of Mike Powell's code is that it starts with a large trust region. The interpolating points are far away, so it's okay to interpolate two endpoints, even though they're noisy. You have a trust region that when you minimize the quadratic model, prevents you from taking really wild steps. And as you approach a solution, you start shrinking the trust region until you reach an interval where you're minimizing noise. And at that point, you're done because you're within epsilon of the solution. They are able, there's no mathematical explanation, there's no proof yet about why this trust region and so on is working well in the noisy case. But our observation is that it does so, although I suspect you can always find counterexamples where it can get tricked. So yeah, so one tries to avoid this, and something happened to my presentation. Because I did who knows what. Okay, so sorry for that. All right, let's step back and say, how should we do derivative-free optimization? One of the requirements I should put is that we only want, and I'm sorry about that again. Okay, now we're in the right place. We should only use methods that make use of past information to create a model of the objective function. What is it that we do not want to do? Something like just a first order method or a random search method, where you search a point, move there, generate another set of directions, find the minimum point, move there, and do not take into account the history. Do not incorporate that to learn what you've done about the objective function. So like Powell's code, it should be remembering past information. The second requirement, it should be easy to apply to a wide range of problems. To least squares problems, nonlinear optimization, one should be possible to incorporate derivative-free optimization into interior point methods, augmented Lagrangian, sequential quadratic problems. I think it is important that they are scalable, modest in linear algebra cost. The linear algebra of the method should be ON. It should be parsimonious in the use of function evaluations, because sometimes they're extremely expensive in derivative-free optimization. And the other time, it should parallelize easily. If we could achieve all of this, then we'd be in a good situation. Finally, the method should tolerate noise in the objective function. So although Powell went into a direction that is quite interesting, our proposal is to do something that is well known and is perhaps the simplest. So our proposal is to create a method that we will see is going to compete against Powell's approach, and it's based on finite difference approximations with an appropriate differencing interval. The key here is to use the right interval for finite differences. Now, once we have good approximations of derivatives for noisy functions, we can use that information in methods that only require gradients. For instance, Quasi-Newton and interior points, one can use Quasi-Newton approximations, augmented Lagrangians. So using only gradients, one can construct, with changes of gradients, approximations to second order information. And those are the methods that we want to consider. We also want to make sure that we can deal with constraints. All right, so the strategy is to invest as much effort as possible to compute an approximate gradient. And then once you have gradients, delegate the construction of the model not to interpolation, but just hand that information over to a Quasi-Newton or a Gauss-Newton method. Their methods are very clever at using first order information and creating a quadratic model. And what is one of the prototypical, the earliest method that does that is Gauss-Newton. And Gauss-Newton, JJ transposed, is an approximation to the Hessian, but it only uses first order information. What is another example of that? Quasi-Newton methods. Just give it gradients and it can construct a Hessian approximation. So this idea of paying attention to the construction of gradients is also implicit in the work of Nesterov and Spokojny. But as we will see in a moment, they focus on first order methods entirely, and I cannot use the methodology of Nesterov in order to construct what we do. We're actually going to look at the coordinate directions, not at random directions, even though the theory would tell you that that's not the best thing to do. Now, why hasn't this been done? The finite difference approach has been dismissed by the optimization community, not by the machine learning community, but by the optimization community, because of a feeling that it is too expensive and maybe unreliable in noisy setting. And instead of that, for some strange reason, the optimization community focused on methods like direct search for a really long time. It's only the direction of Powell that turned out to be very successful. Now, the irony is that while the optimization community was proposing direct search and pattern search methods, users often use a finite difference approach because if they didn't have derivatives, they just called MATLAB or SNOpt or some code and give it only derivative information, and the code would do finite differences. Now, those codes would work well if there's no noise. So the irony is that users were doing derivative-free optimization well in a non-noisy setting by just calling standard packages. But if you inject noise, then of course things will fall apart. And there was a perception that you cannot make general purpose optimization methods based on finite difference. So there was a disconnection between the research community and the users. All right, so let's talk about how to do finite differences. We can do finite differences if we can know or estimate the noise level of the function, the standard deviation of the noise. So then in that case, we're going to compute a partial derivative, a gradient, through finite differences, and EI is a coordinate direction, and we're going to do it in a standard form. And in fact, there should be, in my formula, there's not there, but it should be an HI. For generality, we're going to be choosing a different finite difference interval for every coordinate direction. So let's assume for the moment that we have a standard deviation of the noise, and we're going to call it epsilon f. Then, by trying to do a least squares error, minimizing the least squares approximation, you end up with the choice of interval is this for forward differences, is the square root of the noise level divided by the maximum value of the second derivative in the interval that you're computing the approximation. Now, the accuracy of your gradient is proportional to the square root of the error times that constant. And it's that noise level to 2/3 for central differences. Okay, so you're statisticians. How do you compute, if you have a function, how do you compute the standard deviation of the noise? Well, I mean, you can do sampling, and in the deterministic case, we can use a Hamming table. But I'm not going to talk here about how you estimate on the fly the noise level of the function and how you deal with the case when the noise level actually changes as you move along. All right, so here's an example. We have this dotted function is a nice quadratic function. We add uniform noise. The noise level is 0.25. And so the theory tells you that the finite difference interval should be about 0.28. And if you choose it in that manner, you find out that the derivative estimate that you get is a good representation of the derivative of the function in that interval. If you choose it to be too small, then it's possible to find regions of the function where this slope does not represent that slope, and that would be a disaster to be doing finite difference approximations. So you have to be very careful in getting the finite difference interval correctly. And by the way, in this formula where we say that it has to be the square root of machine epsilon, there's a constant also. The constant is a second derivative. This is going to be important. This could be a factor of 2 or 3. Even though it's a square root, we have to get it right in some examples. So finite difference is not trivial because we have to also do an estimate of the second derivative here. In some problems, you know, if it's of order 1, it does not matter. But if it's larger, become very small, your algorithm is going to have to deal with this. And we spend a lot of time on that, on automatically estimating this constant here so we can get good finite difference intervals. All right, so an alternative is to follow Nesterov-Spokojny and do Gaussian smoothing. So let's see how does it compare with what they do. Well, their idea is simply to deal with a noisy function, you sample in a small neighborhood, and then you take an average. So you compute a smooth approximation of the objective function, and then define your approximate gradient as the gradient of that smoothed function. And that gives you this formula here, which really means that you take a random direction, mu j, and then do a finite difference with a small interval delta there. And that's going to be an approximation to the gradient. If you do it once, it's a very crude approximation. If you do it multiple times, m times, is going to give you a more accurate approximation. And so you can choose what the value of m is. And in this zero order method of Nesterov-Spokojny, then you're given delta. You simply, at every point, compute an approximation of the gradient by Gaussian smoothing. You move a negative of that direction by some step length, and then they're able to establish some very extensive results, a very impressive paper. This paper of Nesterov-Spokojny theoretically is a very impressive paper because they're able to establish complexity results for non-smooth problems, for smooth problems, and a wide variety of problems, convex, weakly convex, and so on. So theoretically, this is a very important method, but it's just first order information. So in the method of Nesterov and Spokojny, you evaluate the gradient, you move. You evaluate the gradient, you move. You do that 10 times, and you're doing a pure Markov process. You don't see what happened before. So we want to build knowledge based on the changes in the gradients that you have seen. What we want to do is we want to construct a quadratic model and define a second order method. And you could do that with an approach that uses random directions, but this is not going to be optimal in practice. So we're going to press and incorporate more information. Now, what we're going to do, so what I'm going to do is describe a Quasi-Newton method based on these approximations. what I'm going to do does not have better complexity properties than the Nesterov and Spokojny method. In fact, it could have weaker convergence properties. So I'm going to take here a minute to give some personal observations about how worst case complexity has been used and misused. First of all, worst case complexity is a very important field. We know that it has led to revolutionary algorithms such as an interior point algorithm. It really can illuminate the field of optimization. For instance, the class of self-concordant functions comes from doing theoretical analysis. But worst case complexity is often overworked with little impact. So we see dozens, if not hundreds of papers about Nesterov acceleration and cubic regularization. And it turns out that maybe those papers have little impact. So since I'm a practitioner, I'm essentially interested in creating algorithms that people will use. From what I know in my experience, I have never seen a case where Nesterov acceleration is something I would recommend. That sounds like a strong statement, right? I'm not sure of a setting in deterministic optimization where I would recommend using Nesterov acceleration. Why? Because there are superior algorithms in practice. Nesterov acceleration is going to be the best in the worst case. In the worst case, that may never happen, right? Now, it is superior clearly by that measure to the gradient method. But what is the gradient method? What step length should we use? Well, 1 over L is the most conservative strategy. And you really don't want to use 1 over L always. So people sometimes ask me, how should I implement the gradient method? How do you implement the gradient method? And I always tell them, you know, I don't have a code for the gradient method because I never use the gradient method. We have better possibilities. The step length could be determined by quadratic interpolation. It's expensive. So selecting the step length has been a quagmire for the gradient method. It's been an issue that has been unresolved, but an issue that really went away with the advent of Quasi-Newton methods. Then you don't have to worry about that anymore, because once you know how to scale a direction, you can take unit step lengths most of the time, whereas the gradient method, the pure gradient method, has no scale. And this is why you're constantly struggling about how you're going to choose that step length. Machine learning, stochastic problems is a different issue because there's a possibility of getting very, very cheap gradients, and you should do that. So worst case complexity, for instance, misses Quasi-Newton entirely, because Quasi-Newton not only appears to be not better, but inferior in the worst case. Cannot prove it to be better, but everybody knows by that some other measure, and worst case complexity is not the only measure. If you use, for instance, local convergence, a Quasi-Newton method is superlinearly convergent using only gradients. And it turns out that it's more effective in practice and more scalable. So sometimes worst case complexity misses entire classes of algorithms that we should use. So just to summarize, and I believe that Steve Wright is going to talk about this more extensively in some talk soon, worst case complexity is something that should be understood as one measure and only one. There are other measures that can lead to 3 possible outcomes. Sometimes it really succeeds in the creation of practical methods that people will use. There are cases where it's not able to distinguish between methods that are good. I would add cubic regularization and trust region methods. It's not able to differentiate. For instance, if you compare Nesterov acceleration with the conjugate gradient method, it's not able to tell you that in the worst case they're similar, but in practice, if you have structured the conjugate gradient, it's going to be highly superior. So sometimes it's unable to distinguish between methods, and sometimes worst case analysis simply misleads by giving the impression that first order methods are optimal, No, they're optimal by that measure. So this gives the impression that things like momentum are useful in machine learning because of their relation to acceleration, whereas the use of momentum has been useful in machine learning because it improves the statistics. So things get confused because worst case complexity is given such an important role. In our next edition of the book, Steve Wright and I are going to work hard to try to put together an analysis of how many of all the methods we cover in the paper are actually well categorized by worst case analysis and which ones are not, and similarly for other techniques. In any case, let me do some testing about methods that estimate derivatives of noisy functions. We're going to look at unconstrained, nonlinear least squares, and constrained optimization. And for unconstrained problems, we're not going to use a gradient method. We're going to use a finite difference, Quasi-Newton, LBFGS. And we're going to compare this with this code, which is the best code produced by Powell using interpolation. We're going to do nonlinear least squares. This is a recent code by Roberts, and it's of the Powell type. And what we're going to do is we're going to take a classical MIMPAC code from the 1980s and put robust finite difference methods to that and compare the two approaches. And then for constrained optimization problems, we're going to take our code Nitro, compare it to the code developed by Powell, which is put robust finite differences within Nitro. And by the way, we're going to use the weakest, the least efficient version of Nitro. Nitro offers 5 algorithms or so. We're going to use the least efficient, infuse it with finite differences, and compare it to this DFO method specifically designed not to approximate gradients. So in the unconstrained setting, which is the only method I will describe, you assume that you can estimate the noise level. With that, you can compute a finite difference interval. So implicit in this is that you can also approximate L, which we discuss in our paper. Once you have a finite difference interval, you get a gradient, then compute a Quasi-Newton direction and perform a line search. So you're going to be updating a matrix HK, compute a Quasi-Newton matrix HK updated, and move along this direction. And alpha K is going to be determined through a line search. So we're not going to do a fixed step length, or we're not going to take one. We're going to require that the step length provides sufficient decrease in the objective function, and that as you move the derivative, you will not stop with the line search until the derivative starts increasing. This means the directional derivative has increased. These are called the Armijo-Wolff conditions. We're going to put them in there. And because you can never be sure that your finite differences are correct, you need to have a corrective procedure so that the line search fails. You have to go and re-estimate the noise level and make sure you can get a correct rating. So the line search plays a dual role. It determines how far you go, and there's an indicator as to whether you got the finite difference interval correctly. We need to determine the noise level, and L should be re-estimated if you have difficulties. And I wanted to make a comment here, but maybe I have written it later. Okay. There's a big problem with what I'm proposing here. We're proposing to do a Quasi-Newton method with noisy gradients. And if you get the noise level wrong, it looks like that's just disaster. You're going to be very careful. Quasi-Newton method looks at changes in the gradients to construct a convex model. If one of the gradients is wrong, you get a very bad model. So is Quasi-Newton stable? Well, one of the papers here with Duchenne is they did the first analysis of Quasi-Newton methods under the noisy setting, and we show that with a small modification it can be made stable. I will mention that in a moment. Now, BFGS, something that's not appreciated very much, is that Quasi-Newton methods although they look at the whole past history, do not create conflicts because BFGS is an overwriting process. No inconsistencies or ill conditioning will arise because if you give the same information twice, it's going to be the second information that is going to update. You update twice, the second update overrides the first one. Why are we using standard Quasi-Newton methods in this noisy setting? Why aren't these guys from Northwestern using the same ideas? Why don't they come up with something new? Why didn't we develop regression-based Gauss-Newton or Quasi-Newton methods? Why did we use the classical algorithms? And something that I can say is that we tried not to use LBFGS. We tried to define a new update that instead of interpolating gradients, Quasi-Newton, what it does is interpolates the function and the gradient at 2 points, that it does a regression. And so we tried very hard for more than a year to find a regression-based Quasi-Newton method, and we could never find one that could scale like LBFGS. But that does not mean that it doesn't exist. Something that I wish is that all the talent that goes into doing complexity analysis would go into a design of algorithms and would come up with a whole branch of Quasi-Newton methods that are more tolerant to noise. We found a way to make it tolerant to noise, but there must be other ideas. What we tried simply was not robust as classical Quasi-Newton methods, and they didn't scale. I think I'm not going to mention here very much what this means, but or maybe I should. I'm going to compare. So we're going to compare what? This is Powell's code, the best thing around, in my opinion. And this is just a finite difference LBFGS method that we proposed using a finite difference interval, which is proportional to the square root of the noise error. And what we do in this axis here is we label all the problems. For each problem, we're going to produce a graph. The graph does the following. You see how many function evaluations you took with our code and how many function evaluations with Powell's code. You look at this ratio. So good means that this number is less than 1, implies that the log is negative. So every time you have a negative number here means a problem where the proposed algorithm won, and a bar corresponding to positive number means the Powell method. So although Powell spent many years developing this method, for the noiseless setting, we find out that doing robust and careful finite differences beats it. Interestingly, if instead of finite forward differences, you do central differences, then this area is bigger, meaning that there is a factor of 2. You can't, within a factor, central differences is twice as expensive. If you take a finite difference method and make it twice as expensive as it should, you're no longer competitive. Otherwise, you're very well in there with a very simple strategy. We've done nonlinear least squares, good results. We've done constrained optimization, good results. And I don't want to spend much time on the numerical results, but just mention the following. In the noiseless case, none of the DFO methods in the literature are superior to finite differences, in our opinion, as measured by function evaluations and accuracy. The great code of Mike Powell is not faster than a good finite difference LBFGS code. In the noisy setting, for nonlinear least squares and constrained optimization, finite difference approach is as good as those established methods. But for unconstrained problems, Powell's neural method is superior to what we proposed here, but not by a wide margin. An open research question is how to bridge the gap between the two methods in the noisy setting, and these young people are working quite hard on that. And I'm confident that that gap can be bridged. But there's an interesting thing, and that is that this Powell method that interpolates, it's actually surprisingly good in the case of noise. Now, since this is a talk about mathematical foundations, I want to talk just a little bit about analysis in the 5 or so minutes that I have. We cannot just be proposing heuristical methods. We need a theoretical foundation for them. Estimate gradients to finite differences. Can we do that formally? Sure, there's a theory for that. Can we incorporate second order information and prove that what we're doing is robust? That we need to do. Can we make the method adaptive so that when a finite difference interval is incorrect, we get a notification or some diagnostics of it and can go back and do a finer estimate? So our ultimate goal is not to prove worst case complexity, but to establish convergence results, deterministic convergence results based on a bound on the noise level to a neighborhood of the solution that determines the noise level of the function. So if the optimal value of the function is 0 and the noise is here, we want to make sure that the algorithm converges at a very good speed to this band of the solution. So we need to identify the algorithm components that need to be redesigned. And we note that it's going to be important to do a change in Quasi-Newton updating. We need to lengthen, we may need to lengthen the interval where we measure difference in gradients. And for constraint optimization, there's a merit function that guides progress. This is a delicate thing. It has to be redesigned to be robust in the noisy case. Okay, so doesn't the BFGS make breakdown when the function and gradient evaluations are inexact? Yes, it does. If so, is there a way to make it stable in the noisy setting? And to our knowledge, nobody had looked at this question, because in fact, the analysis of Quasi-Newton method is quite complex. So we showed that a natural simple modification is guaranteed to converge linearly to convergence of the solution, and there are no tricks, there are no parameters there that you do not know. Just in pictures, what is the problem of doing Quasi-Newton methods when there is noise? Shouldn't at least they be okay when the gradient is big enough compared to the noise level? And the answer is, if you do Quasi-Newton methods, you may get into trouble at any moment. So what Quasi-Newton methods do is they look at the difference in gradients. Gradient at the new point, gradient at the previous point, you subtract them because the difference is an estimate of the derivative. But if you have noise, and if these two quantities here cancel each other, suppose that you happen to take 2 steps and the gradients are almost the same, either because the step is really, really short or you were unlucky. Then if these 2 points cancel out, what you're doing here is differencing noise. You difference noise, you put it in the Quasi-Newton approximation, and unless it's overwritten, you really created some really damaging, really some harm there, and the method is going to be really poor. So you cannot allow finite differences that are smaller than the noise. You cannot differentiate noise. So they redesigned the algorithm so that we want to make sure that once the error dominates, it should never take wild steps but go to that region. And we're able to achieve this. So this is what happens when you run BFGS method without taking any precautions. This is a simple problem. This is the norm of the gradient, of the true gradient. And these are the iterations. So here's a run where BFGS is working to some degree. The noise level, I think, is 10 to the -3. It does approach a solution. And over here, we have a condition number of the Quasi-Newton approximation HK. And we see that it blows up 10 to the 14. That's not good. or once you have a matrix that is like that, you don't know what's happening. What we want, and we achieved in our paper, is the following. Here is now the difference between the true function value and the optimal function value as the iteration progresses. And we use the case of intermittent noise to try to confound the algorithm as much as possible. So in this example, we have a problem, a test problem that is well known, an eigenvalue related problem. And we put noise and then don't put noise. And then put noise and not put noise. So that if the algorithm is such that it's based on regimes, it's going to get confused. Well, what we're able to do is this. Classical BFGS stagnates. The intermittent noise is going to create bad matrices, large condition number. It cannot make progress. Once you create very bad steps, the line search is not going to allow you to move, right? And the modifications that we have, L stands for lengthening, what they're able to do is they're able to get to a good solution. There is a stepwise behavior because there is intermittent noise. And now, instead of, this is the condition number of the problem, by doing our BFGS extension, we keep the condition number low, whereas in the past it was going high. And I will just mention how you do that. There's only one small modification. Apply the standard Quasi-Newton method with a line search and monitor the length of the step. If the length of the step is sufficiently large, L, so that you're not going to be differentiating noise, proceed as usual. Standard Quasi-Newton algorithm. Otherwise, take the step. But before you update the Quasi-Newton matrix, lengthen the interval that measures the curvature. So the difference in gradients is not going to be at the iterates, but you're going to take a displacement of order L. You want to make sure that you're differencing at the points of order L. And L, the theory says, it's of order the error in the gradient divided by the strong convexity parameter. So this is an analysis for convex, strictly convex problem. And as a guideline, it tells you that the length of the updating procedure should be proportional to the gradient divided by a strong convexity parameter. Now, this is theoretical because you need the strong convexity parameter. And in our second paper, we get rid of that. If you do that modification, then the algorithm will be practical, will be stable. And this was published in a SciOp paper. And the proof, which I will not go into this because Quasi-Newton is quite complex. The proof, which I have in the slides, it's really mainly due to Yu Chen, our student here. With some guidance, he was able to expand some analysis we did in the 1990s. And here's what the convergence analysis looked like, and you don't want to get into all the details. I should just mention one thing. In Quasi-Newton methods, you generate xk and hk. So you would think that in order to prove convergence for a method that approximates Hessians, you first want to prove that these Hessians are well behaved, that their norm is bounded, that their condition number is bounded. So you would say the proof is this. I'm going to look at the algorithm and prove that the Hessian approximation is as a bounded condition number, and then I show convergence. It is not possible to do that for Quasi-Newton. For Quasi-Newton, you only know that the Hessian is well behaved until you've shown convergence. So you'd have to do the two things at the same time. You have to simultaneously prove that this is approaching to the solution, and then you can see the Hessian is not ill-behaved. And that's what makes this analysis kind of difficult, and this is why I'm skipping it. I finish here by mentioning that when we run the code, it uses the standard, this is the standard method. And when does it start deviating from this? When does it start lengthening the differencing of Quasi-Newton directions? When you get to near the noise level that's when it starts doing things. And this experiment shows also that. And by the way, one last thing that we show is that suppose that the optimal function value is 0, and that this is the noise level. We show that the algorithm approaches this neighborhood linearly. And once it gets into this interval where noise dominates, the algorithm cannot make things worse by another epsilon. It is at most 2 epsilon away. And that means that your Quasi-Newton matrices are struggling because you're giving it noisy information. But our lengthening procedure stabilizes well enough so that you may create steps that take the true objective. This is phi. The noisy objective is always decreased, but the true objective will only go up by a factor epsilon from where you are because the condition number of the problem is controlled. And that is in the proofs. That is inherent in the analysis that we have in those papers. Those convergence results are established. To finalize, we think, like many people in machine learning, that doing finite difference is a good way to do derivative-free optimization, even in the noisy setting. We have now written papers that cover not only the unconstrained case, but also least squares and general constrained optimization problems. We've done experiments where both the function and the constraints are noisy, and we do approximations to both of them. And we find out that finite difference approximations are a very promising way to go. They're quite delicate. But optimization provides a more benign environment than in applied math. So finite difference methods is the bread and butter of applied math. In differential equations, you have finite difference methods. And you have to be careful. The error that you make adds up. Optimization is a different setting. In optimization, if you compute a bad step, you may correct it the next time around. The errors do not accumulate. It's more benign. Nevertheless, you have to be quite successful to make this work in practice. And to conclude, this algorithm that I proposed here, by a worst case analysis, would not be better than Nesterov and Spokojny. But you run experiments, and it's going to be way faster than that. All right, I'll finish my presentation here.
Thank you, Professor Nocedal, for the great talk. So now maybe let's look at the questions. So the first question is about curse of dimensionality. So how does this method, finite differencing method, or DFO in general, depend on the dimensionality of the space of the input?
Yes, well, in terms of arithmetic, the arithmetic cost is of linear in the dimension of the problem. But each iteration requires d function evaluations. Now, it sounds like a lot, and this is why it was dismissed. But what matters in the end is how many function evaluations you do total, right? So, so that's the way. And we cannot put bounds. Worst case analysis bounds we do not have on the number of function evaluations. We don't bother to do that because Quasi-Newton is always going to give you worse than Nesterov and Spokojny.
Thank you. And then another question is it possible to do zeroth order or finite differencing in mirror descent?
That I'm sure that needs to be thought out carefully. I haven't thought about this. It's a worthwhile question.
Thank you. And another question is, for the finite differencing method, what if there are some constraint in the input? for example, the input space lies in some Riemannian manifold, then it's possible. Then the finite difference seems to be a bit complicated because you need to do some exponential mapping. Then is there a way to do a similar finite differencing method in optimization on manifolds?
Yeah, another very good question. I think it is possible. I have not done it. I have not thought about it. It's worth looking into.
Mm-hmm. Thank you. And also another question is, could you please comment on the generalization accuracy of this type of algorithms when applied to machine learning in comparison with SGD or ADAM methods, maybe theoretically and empirically?
Yeah. So no, all this work is not done in the context of machine learning, right? So I have no such results, and this is geared in a different way. Let me put it this way, just to set the stage about why we're doing what we're doing. Since I'm saying, I have nothing to do. There are people who are doing all sorts of applied math computations. They're looking at fluid flow, combustion. There are tons of codes in engineering. And in all of them, a code contains another code inside. Another code inside may do things inexactly, right? So the total function evaluation is going to be inexact, right? So I'm not looking at machine learning codes. This was motivated by the deterministic case, right? And so what you have there is function values have noise. And if you just plug in standard codes, they would break down, right? So we're looking at that setting. Does any of these ideas have value in machine learning? Well, for a while, we were trying to extend the idea of Quasi-Newton to SGD. And I don't think any of us really succeeded in getting a good algorithm in that context, right? Not to mention even generalization problems, even to make it work well in practice, right? So yes. Finite differences have no role in neural networks where you get cheap gradients.
Thank you. And there's a follow-up question. Could you please elaborate more on the application of this finite differencing method and what kind of real problem can be solved by this method?
Yeah, so first of all, the biggest example that we like is the one where you have a code, and inside that code, there is an iterative method to solve a linear system of equations. So almost every PDE code that uses an implicit method will have inside there a conjugate gradient or a Krylov iteration. And in one point, you may do 8 Krylov iterations. When you move a little bit, you may do 9. And so the function values change there. So in applied math codes that have an iterative method inside is the biggest area of application. And we're talking here about some of the most important codes around for applications in climate, geophysics, structure design, and so on.
Thank you. So essentially, it can solve the problem where there's a optimization or a subroutine for evaluating the function, calculating the function values.
Yeah, but that subroutine is subject to changes as you do small perturbations. There are small changes. I'm gonna mention that my battery is now at the limit. So if I disappear, it's because the battery died, right?
Sure. Okay. Sure. And maybe we'll just finish in a few minutes. So there's a question asking, can you combine preconditioning techniques with this method?
Yes, I mean, in some sense, Quasi-Newton is one way of preconditioning, but not the only one. And in our least square study where we use Gauss-Newton, there you can improve things through preconditioning. The key is that once you have reliable gradients, you can do many things.
Mm-hmm.
Definitely. And the precondition is going to be problem dependent, right?
Mm-hmm. Yeah. So I guess that's all the questions we have. And thank you again for your time and for your great talk. And thank you so much. And also, we would like to thank the audience for attending today.
Well, thanks very much for the invitation. Good to see you all around, and good luck to you guys with your research.
Thank you, and look forward to seeing you in the future. Thank you.
Thank you. Bye.